Good afternoon and welcome everybody to No Compiler Required Hand-Rolling C++20 Coroutines in C++17. My name is Johannes Kalmbach and as you are now all here, of course we are going to require a compiler. First things first, there will be a lot of code on the slides. This will be the minimum font size. In case that is too small, you can either sit closer to the screen or you have two options to follow along the slides. Those are also linked on the Discord in case you want to switch later. I've been programming in C++ for now roughly 10 years. Currently, I am a PhD student in hopefully the last year of the program in Freiburg in southern Germany. And in my day job there, I develop the clever RDF and Sparkle graph database. So if you're interested also in those things like data management, semantic web technologies, you can also come talk to me. And the most recent thing that we did is from that open source project that we did, or that we are developing, is we founded a small company that tries to commercialize or to give commercial support for our open source graph database and hopefully make a living out of this. So, as said, we have an open source project and it is currently developed in C++20 and is publicly on GitHub. So one day we get the following request. And at first we thought, okay, every now and then somebody asks, have you considered rewriting everything in Rust? And now we obviously also have people that want us to arbitrarily switch our C++ standard to something older from the past, which obviously is a lot of work because we were using C++20 or still are quite liberally, so everything except for modules. But then, some weeks later, this request got more concrete and more like a business proposal. Because now in the meantime, it was C++17 what they wanted, not 14. It was also just a part of the code base. They were willing to contribute some resources. And so we thought, this is now a good opportunity for our newly founded company. Let's do this. And this whole migration is an interesting story, but that is a story for another day. But what we are focusing today are coroutines, because we also obviously had some of those. So first, I'm going to quickly show you how we did it in the actual project, and then for the rest of the time, we'll do something completely else. So our solution that we did was mostly what you see here on the right side. You have a generator, and a generator is an input range, so you write a function that just, when being called repeatedly, always gives you the next value, and once you are done yielding values, you return a null opt, and then you inherit from some base class this on top of this get method, gives you all the iterator boilerplate that you require to be a proper input range. So we used approaches like this. There were some variants of this, and this project is now done. It works, but looking back at it, I'm not 100% satisfied with the results for two reasons. The first one is the code got much less readable because in the C++20 coroutine generator world, a lot of the boilerplate is handled automatically by the compiler. You never get to see it. But in this solution, all these things came back to the light. And even more seriously, while doing this, some bugs arose in this rewriting. In the meantime, we hopefully have all fixed them. But the reason behind this was that mostly this rewrite was done by the external developers from our partner company. And as those obviously in their day jobs are not really working on C++20, they also are not that familiar with the details of the coroutine semantics. And you need to understand something. Even if you migrate from something, you also have to understand the details of the thing you're migrating from. And in C++, object lifetimes is always one of the first things where things can go wrong. So when reflecting on this, I thought, okay, is there a better way to do this rewrite? And by better, I especially meant more generic, or finally even more automatic, because our solution required to individually look at every coroutine, find an individual solution for everything, and maybe we can do better. Then I did some experiments. I tried some things. I found some things out. I fell into a very deep rabbit hole, and what I found in there is what I'm going to actually now share with you. So what are we going to do now? The first thing is a quick introduction into coroutines, like only the minimum that you need, mostly the infrastructure, and then the biggest part will be we'll have some examples of concrete coroutines, and we will implement an infrastructure and a way to manually lower them into C++17 compatible code with hopefully the same semantics as they are specified in C++20. Then we will think quickly about that we're not bound by the C++20 standard, but with slight changes in our infrastructure, we can also implement our coroutines a little bit differently with different characteristics. And then, as the last part, I'll show you a demo because, as you see, part 2 is something it's emphasized that it's manually, but to scale something, it's very generic. We want to do it automatically, and I started developing a tool for this, which I will then showcase. So, what do C++20 coroutines, all the machinery around them, what parts are in there? The first thing, obviously, is the actual coroutine. You write a function, and this function has those special keywords, at least one of them, co-yield, co-await, co-return. And additionally, it has a specified return type, and that return type is important because it tells the compiler how this function, this coroutine, behaves, what the semantics, especially of those keywords, are. So this is what the user writes, and what then happens, what the compiler does in C++20, and what is the most thing that we have to do manually in our C++17 approach, is it takes this coroutine, this function body, and synthesizes from it the actual state machine that this coroutine corresponds to, because like a coroutine, you know, is a suspendable function that can suspend and then later continue where it left off. And this is, under the hood, transformed into a state machine. You see here this coroutine frame is the data that you need for the state machine, as well as also the functions. So you have in there a lot of things, which I'll later show you. But important here is this blue synthesize arrow. This is something that we'll have to do in our approach manually and individually for every coroutine, because it depends obviously on the coroutine body. Next, there is the coroutine type, so the return type of the coroutine. And the most important thing that you need there is a promise type. This is mandatory to make a type compatible with the coroutines, because this associated promise type tells the compiler how a type is used as a coroutine. In particular, you have those methods that specify what happens at the beginning, at the end of a coroutine, what actually happens when you yield or await or co-return something, how do you deal with exceptions, and some more things. The good news is, in our approach, that the promise types, which are part of the library of those coroutine types, can stay largely unchanged, because we will implement our infrastructure around such that it can use those promise types as they are. So then this is typically, most coroutine types, this is not mandatory, but they have some interface that actually is the user interface from the outside. So in the case of a generator, it is this iterator interface that makes the generator an input range. So you need a begin and an end method. And the question is now, how do you implement this? Because if you think you have an iterator, you advance the iterator, you somehow need to tell your coroutine, your hidden state machine that the compiler wrote for you and that you don't know much about. You have to tell this, okay, please continue until you have reached the next value that is yielded such that I can report it via this iterator interface. And this is done by the type std coroutine handle, which is a library type in C++20 that heavily interacts with those compiler synthesized coroutine frames, because it allows you to control them. In particular, it has those functions to resume a coroutine from one suspension point until the next suspension point, to destroy a coroutine while it is suspended, to get access to the promise object, because every coroutine frame contains an object of this promise type, which you can also get access to and use this to control the semantics, and some other methods. And we will have to implement a generic replacement of this coroutine handle class that works in our rewriting. Now also, what's important here, what is in the coroutine frame? I already said there's this promise object that is always there, and then in the coroutine frame there's the function parameters and the local variables of the coroutine body, because the C++20 coroutines are stackless, and those variables which are in the coroutine body, those they have to survive during this suspension, so they have to be stored somewhere. So they are stored in this coroutine frame, and there's also this concrete and individual for each coroutine functionality of the actual functions to resume and to destroy a coroutine. So this is what we need, and part of it we have to replace. So let's start with a simple example. Here we have one of the simplest coroutines you can think of. It's an IOTA generator. It has, in particular, it has function parameters, but it has no local variables, a single yield statement. And what we will do in the next slide is we will rewrite it to C++17, assuming an infrastructure which you have not seen yet, which we will then fill in afterwards. And important, we will now see a lot of code. The code is slideware, so I've implemented this, but sometimes I've simplified here to have not the syntax that C++ has, but the syntax we would sometimes wish that C++ had. And if you at some point have questions about those details, or doubt that something works, or find a bug that I know of, or find especially a bug that I don't know of, please always feel free to ask. So what we have here, we have our IOTA generator as a state machine. Let's walk through this. First, of course, we still have a function. This returns this IOTA function, still has the same parameters. And now we implement a local class for our coroutine frame. And you already see it inherits via the CRTP idiom from some base class that encapsulates all the things that are common for our coroutine frames. And that is also templated on the promise type that we use. So let's see what's in this coroutine frame. First, we have to store the local parameters. We have an in start and in end as our parameters, so we store them in here. This is a struct, so we can also later just aggregate initialize it if we want to store them in there. And then we also need in line 6 for the co-yield, there's an awaiter object. In this case of the generator that we assume here, it's a suspend always awaiter, and we need some storage for it. So this coro storage, think of a suitably aligned buffer. We'll talk about this later in detail, but it's something you need. So and then we have the actual function. So it's called here the resume impl function that does the actual state machine logic. And in the beginning, we have a switch statement because when we resume our function, we have to know at which point of the function we are going to resume. And this index is an integer stored also in that base class. And for our coroutine, there's actually 2 suspension points. One is always at the beginning implicitly, because every coroutine starts at the beginning and also might suspend there. So this is the index 0, in which case we just start. And then there's the second one. This is our single co-yield statement, which is also then a second suspend point. And I implemented this via goto, because goto, hopefully, no one actually writes in their coroutine a goto statement, so we can use this for our purposes here. And now we have our while loop, which increments, and the co-yield can be implemented also by a macro, which you'll see in the next slide. And the parameters in the macro first, this 1 is like the index of the suspend index. So you can also imagine we have to set somewhere this index to this point, and we have to, at some later point, write this suspend label 1 such that our goto works. So this is the first parameter. The second one is when you co-yield, there's this awaiter object, which we will have to pass in there. And the third one is, as you can imagine, the actual expression that we are yielding. Next thing is that in coroutines, you cannot just fall out of a coroutine, but each time you will just silently end the body of a coroutine. There's an implicit co-return statement. So this was not in a coroutine, but there is some logic that has to be run here. So we have to do something for the co-return which also in this case can be implemented as a macro for the next slide. Okay, then we have defined our coroutine frame. Now we somehow have to initialize it, and therefore we have from our CRTP base class, we have this ramp function, how it's typically called in coroutines, that does all the setup, all the allocations, the initializations, all the construction, and then converts this into a generator type and returns it. The next thing I'll show you is those macros, what is actually involved in co-yielding and co-returning. So let's start with the co-yield. First, when we yield, we see there's yielding means a possible suspension point. The suspension point has this index, so we have to store this index somewhere in our class such that we can remember it. Then what the co-yield does in coroutines, it calls into the promise type. The promise type has the method yield value, where we pass in the yielded expression. And as you see here, all this co-init and co-get stuff means that we have this awaiter now, which is basically placement newt into our buffer, which we have there. That is what those macros do. And then this awaiter object is awaited, which we'll see on the right-hand side of the slide then. And after that, basically in line 5, this co-await call, this might return from the sum function because we might suspend here. So, and when we come back, we need to have this label such that we can then, now our goto works. So it's the suspend label appended by our index. And this is now the part when we come back from the co-yield. After the co-yield, we have to call await resume on the awaiter object. This is something just the semantics of what these coroutines do, what awaiters do, and then also destroy our awaiter. This is also something we see here. We have our things that suspend and that survive the suspension of the coroutine. All those things, those locals, we have to manage the lifetime explicitly. So we have here an explicit constructor call at this point. Okay. What does co-await do? So this is basically textbook similar to what you can also see on CPP reference. So co-awaiting something means an awaiter first has a method called await ready, which returns a bool, which can say, okay, if it returns true, it means this awaitable is immediately ready. There's no need to suspend the coroutine. You can just return. So if this returns true, we don't have to do anything, and the coroutine just continues. But if this is false, then we have to do something. You see here, there's this call to the await suspend method in line 4 of the awaiter, and this await suspend method handles the actual suspension, and it is past the coroutine handle of the actual coroutine. And the rest of the function depends on this type that await suspend returns. Because in the coroutine there's 3 flavors for each awaiter what it can return. The simplest case is that await suspend returns void. And void means unconditionally suspend this coroutine and return control to the caller of, so just propagate it to whatever is above directly on the stack. So here we can just call await suspend, it returns void, and then we just return. For a reason we'll see, we don't return void from those inner functions, but we always return a coroutine handle, which in this case is empty, meaning return control to the caller. The second case is we return a bool from await suspend. This means it can be at runtime that sometimes this coroutine is suspended and sometimes it's not suspended. So the semantics are, if it returns true, it was suspended, then we do exactly the same as in the void case, return control to the caller, and else we do nothing and just continue our coroutine. And this third case is also interesting. This is the so-called symmetric transfer. In this case, we suspend the coroutine, but we do not return the control back to the caller. But our call to await suspend returns a coroutine handle to another coroutine, and this coroutine is then symmetrically resumed. So you can hand off control from one coroutine directly to the other. And for this is implemented in our machinery by just returning the handle to this other coroutine up the stack to the infrastructure, which we'll see later how this is implemented. Okay, so this is what you have to do to co-await an awaiter. And the last thing we saw was co-return, in this case co-return void. And for a return statement, you first have to call into the promise type. There's this return void method where the promise type configures what is to be done when a coroutine statement is encountered. We also have to inform our coroutine that it is now done, meaning that after we've hit a coroutine point in particular, we cannot resume the coroutine anymore, and this can be checked. And then, if you notice, this macro has varied arguments, and the reason is that for a co-return, first we have to call this return function of the promise type, and then we have to destroy manually all the members, all the local variables in our coroutine that are still alive at the point of this return. And this is what happens here. We'll see this later in more detail because our coroutine so far in this example did not have any locals. But this is also something that has to be done here. And then what happens? There's also a final suspend, which is always there. Typically that's something like suspend always. And this is also something that we have to await then. And there's two cases. Either in line 7, our co-await returns, so the coroutine suspends. Then we leave here, and it is from this point the only thing that you can basically do with the coroutine is destroy it externally. Or if this final suspend does not suspend, then immediately the whole coroutine is torn down. Basically, the whole coroutine frame is destroyed. The memory is freed, and at this point you cannot do anything with the coroutine anymore. This is here in this function that does what has to be done. It resumes the final suspend and destroys. And what you also can imagine that we have some more macros. This was now for the co-return void and for the co-yield. There's also co-returns that return a value. Then you obviously don't call promise return void, but the other method for this, and that's also similar to the co-yield macro. There's a co-await macro for coroutines that use the co-await statement, but you have to do similar things there, the most important infrastructure things you have seen in those macros. Okay, yes?
Question, how does destruction happen in this last method, line 8 on the left?
We have already destroyed with the local variables from the coroutine already are destroyed at this point, but there's still the coroutine frame, which contains, for example, the function parameters to the coroutine that are then destroyed. So this whole coroutine frame, also the promise type is in the coroutine frame. This is destroyed, and then the coroutine frame is heap allocated or somewhere allocated, and this allocation is then freed. This is what.
So but physically it's like delete this or what? Because there is no parameters, I see. Okay.
Yes, those are all called from member functions, so those are all member functions that have this parameter, which is the coroutine frame. So this line 8 ends with something like delete this with some configurable things, yes. Okay, we've seen this, what we roughly do with the coroutine bodies. Now we need also our coroutine handle class and our common base class for the coroutine frame. And this will be the next part. Here we see the first part of the coroutine handle. First thing, so forward declaration. The coroutine handle is templated on the promise type, but sometimes it can also be templated on void, in which case it's fully type erased, pointing to just any coroutine. And the first thing is here this ABI type, which is 2 function pointers, 2 type erased function pointers, one to a function that does the resume, and one to the function that does the destroy. And this is also very similar to how it's actually implemented at least in GCC and in Clang, that you have those 2 function pointers which are stored in the coroutine frame, and then just do that required type erasure because the coroutine handle is fundamentally type erased. And then in the coroutine handle, we store a pointer to this ABI type. Note we could, in principle, also store the two function pointers here, but with this additional indirection, this coroutine handle gets as lightweight as possible. It's basically just a single pointer. It's the lightest handle you can get. And also one thing that is here, you again see that this resume function pointer does not return void. In the implementations of GCC and Clang it does. The reason is again this symmetric transfer, which we'll implement here in this coroutine handle. The actual compilers do it a little bit differently, basically with a mandatory tail call optimization. But that is, if you're not the compiler, it's a little bit harder to enforce tail call optimization in all cases, so I'm doing it a little bit differently. So what can we then do with this pointer? We have the functions that we need. So resume is on the next slide. Destroying is just calling into the corresponding function pointer for destruction. A coroutine is done. There's this interface that you, in the coroutine frame, this convention that you set the resume function pointer to 0 to say this coroutine is done. You may no longer resume it. And a coroutine can also be, a handle can also be completely empty, meaning that it does not point to anything. And the rest is on the next slide. Before we see the resume function, there's another case, because a coroutine handle, if it is templated on a promise type, so not on void, then it also, there's functions from the coroutine handle that points to a frame to access the promise object inside that frame, and also the other way around, from a promise object that is inside this coroutine frame, get to the corresponding handle. And how we do this is that we have this, in our coroutine frames, we will put them right next to each other. So we will put a member of this ABI type with the function pointers and then the promise type right next to each other. And then in practice, we can do this calculations with some offset alignment things. I'm sure there's something that is, according to this standard, not guaranteed for types that are not simple enough, but in practice it works. You can static assert that this is correct. And I'm also fairly sure that after this reinterpret cast, there's at least a step longer or something missing. But yeah, in practice, it works for me. So, the thing that remains is resume. For resume, we just call the resume function pointer. And the only thing that is missing is that we have to handle the symmetric transfer. So this resume, this returns another coroutine handle. And if this coroutine handle is empty, this means return to the caller, break out of the loop. And otherwise, if we get symmetrically transferred other coroutine handles, we keep in this trampoline style, we keep on resuming them until at some point we're done. So this is the only complexity here, is that at this point we have this symmetric transfer, which will not be a large part of the remaining talk, but if you're interested there's this excellent blog post by Lewis Baker. I can also recommend this this blog if you're interested in coroutines, because it gives like a compact overview on everything that is to know there. Okay, we have a coroutine handle. We still need for our coroutine frame this common base class. First thing we saw, it's implemented using CRTP, so it inherits from the derived concrete coroutine frame class as well as from the involved promise type of the coroutine type that we are writing a frame for. Then is what I just saw. This is what we need to make our coroutine handle work. We have first our ABI thing, which is the first member, so which also means that from the pointer to this, from the address of this ABI type, we can also get to the pointer of the whole frame in our, when we resolve our type erasure. And directly next to it, we have this promise type object such that our offset calculations from 2 slides ago do actually work. Then we already saw this. Every coroutine frame has this suspend index such that we know if we have suspended and resume where into the coroutine we have to jump in our switch case go to cascade. then there's two things that every coroutine has. Every coroutine has an initial suspend and a final suspend, and for this we have an awaiter and we have memory for this. So in general, there's a lot of things that we could get rid of because types are empty or types are trivial. But for the sake of clarity, for everything I have all the calls and all the buffers there. But of course, you can do optimizations. For example, if often the initial awaiter and the final awaiter are the same type, if they're both suspend always, which is anyway an empty type, then yeah, you could deduplicate some things there. And then we have three functions. The first one we saw, this is the ramp, so the whole setup, which takes the arguments to the coroutine because it has to somewhere store them in the frame, so the parameters of the function. Then we have this resume function, the actual coroutine state machine. And we have a destroy function which does the same, and we will see them now. So this is basically all the things you have to do when a coroutine is set up. So the first thing here, first you have a allocation. Coroutines are stackless. They have their state on the heap or allocated somewhere. So you have to allocate it, and this allocation can be customized because the promise type can give you a custom allocator. So we have here this promise allocate function that does the right thing and at the end gives you a suitably aligned and sized memory for your coroutine frame, into which then in line 8 you place menu into this buffer your coroutine frame, and we assume that our derived class then has this constructor can be constructed from its actual arguments. That's what you see here, and I'm sure that in this setup functions there's some exception handling not right, because there's things that, like, if this allocation fails and stuff, we have, of course, or if this constructor does something, there's some slideware involved here. So now we have a coroutine frame somewhere in a heap via a pointer. And then the next thing, this is just how coroutine works. You go to the promise type, which is now in your frame, and call this getReturn object, which gives you typically your coroutine type, like it gives you your generator, or at least something that can later be converted to this generator at this point, and you have to store it on the stack for now. And then the next thing is you have this initial awaiter, and you await it. So this is similar to what we saw before for the final awaiter. You call the initial suspend method, and then you have this boilerplate to store it in this buffer that we've reserved for it. And then what is also nice in line 18, this is a variation of our co-await macro, which has now the semantics that if we return from this co-await, so we await the initial awaiter, and if the initial awaiter suspends and would return control back to the caller, then at this point we have to return this return object. So that's why this macro here, co-await impl has as a last point this return object, such that it knows when I have to return the control, then I return this control object.
Question.
Yeah?
In line number 5.
In line number 5.
Why do you have to pass the coroutines?
That is, the promise type can customize allocation on the coroutine args, because think of you have a custom allocator, and in your coroutine parameters you have, for example, the first parameter is like the allocator or a memory resource, and that this parameter can contribute to the allocations. We have this here. So there's a...
So then the frame also will need that coroutines to be passed along. Because I can understand for the frame, because that is actually the placement happening over there.
Yeah, so this is... Yeah, so in the typical case, is if you just don't have a custom allocation, then in line 4 it just ignores those arguments and just as a malloc on the heap, basically. But you can customize it.
Passing those stuff, it's actually copies happening in line number 5, right?
this promise allocate function takes them by reference and does whatever. Of course, it does it.
It's not a perfect forwarding, right? It's not a perfect forwarding. It's doing something.
No, it's not forwarding, but we better also would not. We should not move out of them because we later need to store them also in the frame. So that is yeah. But this is This is something I've hidden here, but yeah, you have to take care of those things because you can use them for allocation, but you later still need them. Yeah. Okay. And then there's again two cases because you will always have to think in line 18. These await macros, they might suspend, in which case they return from this function, but they also might not suspend. And in this case, we first resume the coroutine, and then when it first suspends and returns control to us, then we return this return object back to our caller. So this is really similar to also what the compiler generically does for every coroutine, because that's just the rules of C++20 coroutines minus inaccuracies because of slideware or oversights, but yeah, that's what happens. So this is the ramp. Now for resuming, as you maybe can think, for resuming we cannot do much in the base class because the actual resuming depends heavily on what the concrete coroutine body does. So the only things that we can do, first of course we get our type erased pointer and have to resolve it to via some computation to the pointer to our actual this object basically, and then we can only handle the case if this suspend index is 0. Then this means we have this initial awaiting point for the initial awaiter that we always know. If we resume from this, we have this initial awaiter that was suspended. We have to await resume it and then destroy it. And else, the only thing we can do is we delegate into the derived class and say, please, you do your resume thing, whatever it is that has to be done. And then the thing we still can do is handling exceptions, because exception handling, we'll talk about this later. If an exception escapes from the coroutine body, then the following happens. You catch the exception, you first have to make sure that the stack unwinding happens, that everything in that the stack of the coroutine, the local variables, are destroyed like it would happen with a stack unwinding. We'll talk about this later. This is what this destroy locals on unhandled exception does in line 10. And then we call into the promise type, we call the unhandled exception method, and it's important that we do this from inside the catch handler such that this method, for example, still has access to the active exception and can do something with it. And then this means our coroutine has encountered an exception that has not been called. So this means our coroutine is done. So we have to say, okay, coroutine, you are now done. We set this, in line 14, this was our interface for this. We set the resume function pointer to the null pointer such that the coroutine handle knows that this coroutine is done. And at the end of a coroutine, we await the final awaiter again. And as you already saw for the regular end of the coroutine, it also there's these two cases, and if this final awaiter falls through, does not suspend, we also have to again do whatever it has to be done. I think my naming was inconsistent here. It's called delete frame. It used to be something else some slide ago, but it's the same thing. If your final suspend, no matter how you reach it, if your final suspend does not actually suspend, you immediately tear down everything and leave down a dangling coroutine handle with which you cannot do anything anymore. Okay, this was resume. And destroy is similar because if we are suspended at the end, this is if our frame is done. But done means we are suspended in our final suspend, or we are in a state where everything is undefined behavior because our final suspend did not suspend, so we can assume this here. If our frame is done, we are suspended at the final suspension point, so we destroy our final awaiter because that's the only thing that has not yet been destroyed in our coroutine. And else, the same as if we are destroying from the initial suspension point, we also know the only thing that we have to destroy is this initial awaiter. But if we are suspended somewhere in the middle, then only the concrete derived coroutine frame can know which local variables are currently still active and have to be destroyed. So we delegate this. And then again, we call this function that destroys our coroutine frame because we are in the destroy method after all. Okay, so now we have seen basically all the parts that we conceptually need to rewrite coroutines that are sufficient for our initial simple IOTA example, but there's some crucial things that we have not seen, namely first local variables in the coroutine body. Then also there's this rabbit hole of exception handling, which also always makes our life hard in C++, and then some subtleties that remain once we have dealt with those big parts here. So let's go to example B. Now we have a little bit more complex example. We have local variables, because here you see it's a generator that takes another range of strings and a string as a prefix. And then for each of the strings, we prepend the prefix and yield the results. So the semantics of this are not really important, but I just want to have something with non-trivial types, where you actually have to, where lifetime actually matters. Because what you now see here, we have variables that live across suspension points. So we have our iterator, our end, those live across the suspension, and what we always also have, what we can easily overlook is that this expression here, prefix plus the dereferenced iterator, it creates a temporary string which is then yielded, and this temporary string we also have to keep alive until actually the suspension returns control to us. This is the reason, this is also important in the coroutines, and this was also where in initial implementations all the bugs were also in the compilers, this things that we have to keep alive that are not super obvious in those yield and await statements. So it's important to not forget this temporary, so we have to do something for this. So how do we do this? We again, for our coroutine, we write a coroutine frame. We have our parameters. This is exactly the same. We have our function parameters. We inherit from the base class. But now our variables are not there from the beginning. At some point in the coroutine they come to life, and at some point maybe they are also destroyed. So we have those deferred buffers. We will talk about the details of those template parameters on one of the next slides, in particular why it has two template parameters, but we now need some buffers for those local variables. And the rest is on the next slide. So what changes when we have local variables? So our switch go to case 0 implicitly falls through. Our case 1, it means our single co-yield point, we jump there. That is exactly the same as for the simple example. But now we have the place where it says auto it equals range of strings dot begin. And here what we do is we have our buffer, and into our buffer we do a placement new. This is this co-init macro. It's basically placement u into this buffer with the result of this expression. Again, the details will be on the next slides, but this is how we transform an initialization of a local variable. Is we use this co-init macro with the name of a buffer that is part of our coroutine frame. And then an access to a local variable becomes this co-get macro, which is basically get me the correct reference type out of this buffer into which I've previously emplaced my local variable. This is why we have every access here with this go-get macro. And this is the same for this temporary. I've made it explicit in 2 lines. We have our string temporary, which we initialize by the expression of the string concatenation in line 11. And then we do the explicit things that we have to do. We actually yield again using our co-yield macro. And after the yield, we also see now this temporary has a lifetime inside that loop. So it starts at the loop body and it ends at the loop body, and we do explicit lifetime management. So we have to explicitly destroy it here in line 13. And also, what we saw previously, our co-return macro has to be passed all the local variable buffer names that have to be destroyed as part of the returning because they're still alive. And this is, in this case, those two iterators. In practice, probably those iterator types are trivially to destruct, but it might be also more complex types, so I said I'd do everything explicitly here. Okay, and what for destroying? There's one suspension index that is inside the coroutine, our single co-yield point, and at that point we have two objects actually in flight. The one is our awaiter from the involved in the yielding process, and the other one is our temporary. So if we are suspended at this co-yield point and we destroy the coroutine, that's the two members that have to be destroyed. The other, the initial and the final suspension point, can be dealt with generically by the infrastructure base class. Yeah. So now let's talk about those buffers. What do we have to do to correctly store all types of local variables in our coroutine? So the first thing that is important, that it has two template parameters. The one is the reference type of the buffer. Basically, if you have this, if you have a member and you access it, there's some reference type depending on how it's declared, but there's a second parameter that tells us whether this storage actually owns an object or just points to one. And this, it's important to understand that those have to be two separate things, because we have this case of we have a reference, for example, a const reference or an array value reference, but it is initialized by a temporary, and this reference has to keep the temporary alive. So we have something that is a reference, but under the hood has to make sure that this temporary object stays alive. So that's why we have this explicit is owning parameter. And what happens if we are owning, we store an object, else we store a pointer to an object. Then what we have here, we have a suitably aligned buffer with a suitable size for whatever it is we need to store. Then here in line 8, we'll see this on this right-hand side. The emplacement into there is done via placement u in a macro. But there's this function that gets you out, assuming I have an object in place there, I get this out. This is important. Again, here you need this esoteric std-launder function, and the reason is that although at the address where buffer is, also we know that there is an object of type storage, but buffer does not, the name buffer points to a buffer of characters, not to this object. So we do the reinterpret cast, we get a valid address, but we also have to launder it for exactly that reason. That's like one of the two cases where std-launder is important. And now this is interesting here. We have a get function that from our object gives us the correct reference. So again, if you see line 17, 18, it's basically sometimes we store a pointer there, sometimes we store the object, so sometimes we have to dereference, sometimes we don't have to dereference. But I want you to think about this, we'll talk about this. I don't return the reference directly, I return this proxy object by value, which has the reference as a data member. And there's a reason for this, we'll get to that. Okay. Destroying is just an explicit constructor, a destructor call, something you can do. Now, to access these core storage object, we had two macros which we've seen. So this co-init is basically placement new with two cases. If our storage is owning, then we just call placement new in this into the storage. And if it is not owning, then we store just a pointer and take the address of whatever it is. And it's important that this address always exists, because if it's something that doesn't have an address, then it means we have something R value, a real temporary that we then have to store. So this works here. And our co-get macro is just, okay, we call our get function on our buffer. This returns this proxy object. And then in this proxy object, there's this data member with the reference type, which we then access. now for this design, there's 3 questions. The first is was why this proxy object, why not directly return from this get function the reference, which would be the obvious case? Question 1. Question 2, why I could, instead of this co-init, with the placement new macro, I could also implement like a construct or in-place function in my type, like the standard library containers do. Why have I chosen to use placement new here with the macro, although macros are not a preferred way to do things? And the third one is, if you see here on the right-hand side in line 5, my arguments, I don't put parentheses nor braces here, which means that those have to be explicitly specified by the caller. If you see this looks like, this line 5 looks odd, like there's something missing. And those 3 questions we'll talk about now. If somebody wants to say something or already has an idea about why this is, can also think some time about this.
Well, for parentheses, it's probably because different types have different construction semantics for like curly braces and round braces.
Yes. We'll see this on the next slide. So in some cases, whether you do parentheses or braces makes a huge difference. So we have to somehow distinguish this. That is definitely the reason for 3.
Well, that's the same for 2. Constructor would enforce a particular syntax. Here you're just grabbing tokens and plopping them in. If it compiles, there are like 7 ways to initialize a variable. If it compiles in one of those ways, it's fine.
Yes, and even more explicitly, there's one thing that you cannot do with those in-place methods, and that is copy elision. If you have some function that directly returns a thing and it's not really work. Copy elision from a function that returns like directly a string object into a vector via in-place stack, as far as I understand.
Well, you can't do aggregate initialization. I mean, you can, but you have to choose.
Yeah, but this is just the thing that does exactly the thing that is written with exactly the semantics. So that's, yeah, exactly.
So it doesn't have parentheses on the value case. Should it have parentheses in the reference case, though? To protect the ampersand?
You have to put the parentheses then on the call side. That is, yeah. But you could put them there, and if they were redundant, probably there would be no harm. But yeah, they're also, depending on what you do there, you might also need parentheses there, but you still can put them in the call side. That is correct. It was actually also a bug that I yesterday tried to fix in the automated tool, that to also make sure that this is correctly parenthesized in all cases. Yes, but I also have some example on the next slides, which we'll can go over quickly because most of the things we've already said, except for the one thing about the proxy type. If you see this example on the left, now we have 2 functions here. We have this getString_ref, which returns a R-value reference, and getString, which returns an object. And here we have a R-value string reference, and it's important this do something does not use, no matter how do something is implemented, it never uses move semantics. You would have to explicitly call std_move there. And on the right-hand side, if our coget would just be a function call to a function that returns an R-value reference, then actually the move semantics would apply here, so we'd have a different semantics, and we don't get this if we use this trick with proxy object by value and then the data member, because it's slightly different. That's the one.
Did you have a real place in the code where that mattered? Like, is this an artificial example or like a real bug that you encountered?
I mean, it's It's important because like on the left side is a copy, and if you like in the left hand side you do something with X and you say I know this does not move, I know this takes a copy, and then in the next line I use this object and then I change the semantics here and then it's broken, or what do you mean?
No, I mean like typically I only see r-value references as arguments for functions. I don't see them as members or as local variables, so I'm not sure how I can end up in a place where this bug in the framework matters.
Yeah, but then you are generically, you do autoref, whatever, which might be an R-value reference, so this might, yeah. Actually, typically, like you see this concrete variable of type R-value reference to the string looks like this, a little bit artificial. But in generic code, anything can happen if you do the concrete template instantiation, so we have to take care of this. And also, yeah.
Okay.
Yeah, thank you. And also what you see here, that here, because this R-value reference is initialized also from a reference, so there's no temporary here, so we can just have the second template argument to false, so meaning we are not owning, we just store a reference. The difference is here, we have also our still a reference variable. Here this would also work with if we had const string ref, which would be a more typical case. We have the same issue. We have a reference that is initialized from a temporary, from a pure R value, I think here, from this getString function. So we have to do lifetime extension, so we have to set this owning parameter to true on the right hand side. And also here what you see for this my co-init x, because of the way with the placement u, with getString, I get immediately the full copy elision. The result of getString is directly in-placed into my buffer without having an additional move or something there. And this is what you already said, like is especially for the string. In case you did not know, the first line x consists of 97 times the letter b, because the character a is converted to an integer, is the number 97, whereas the second one actually uses the aggregate initialization and gives you the string ab, and this makes obviously a large difference, so we also have to preserve this difference in our macros. I also experimented with explicit macros like co-init parenthesized and co-init braced, but this was a little bit more concise. Yeah, of this we'll have to get to the exception handling. So last part thing, because for exception handling we also have now here an example, and what it does is takes strings, tries to parse them via s2i, and the important thing about s2i is that it might throw, for example, it might throw invalid argument in case something you try to parse it does not look like an int. So what we have here, we have a generator that has a yield statement inside a try block, and it does try and catch, and this leaves us some problems with what we've done so far. So the first thing is we have our yield, our resumption point, inside the try block, and we cannot jump into a try block because we just can't, because like a try is such try catch does such side channel with exception handling, stack unwinding, that not even with non-portable ASM goto tricks will still won't let you do this, and for good reasons, because it would probably never work. But we can work around this. The even more important thing is the stack unwinding, because like exceptions can happen basically anywhere, in every expression, in every sub-expression, and we always have to like in inverse construction order unwind all the local variables until we hit a corresponding catch clause or we are completely propagated up the stack. And as we do all the tracking ourselves of those variables, we also have to do something there ourselves. Obviously, the actual coroutine implementation knows what compiler it is, how the stack unwinding goes, and can interact, but we cannot do this as we do pure source-to-source transformation. So let's see how we deal with this. So again, we have our coroutine frame. this is now all familiar. We have our parameters, we have our deferred storage for all the local variables with the corresponding correct types, owning or non-owning. And now we have additionally, we keep track. This is then not zero overhead in the happy case, but we have like one bool for each local variable, whether it is currently within lifetime. We could also make this part of the coroutine storage, but this gives the smaller structs. So, but we just manually keep track of what is currently alive. And then we also say, okay, if an exception escapes from somewhere, I cannot really say from where it escaped. So I just, in the reverse order in which I will later construct those local variables, I just check if they are currently within lifetime, then I only destroy them. And note that this function also can never short circuit, because in like nested scopes it might be like that I have some variables from the end which are in lifetime, then some from the middle which are already out of lifetime because they were in a nested scope. So I just check all of them, but this also happens in the unhappy, in the exception case, and in the exception case we are used to some overhead as C++ developers. Okay, what does this have to do? What else have we have to do for our resume function here? Okay, the first thing is we cannot jump into our try block. So what we do is we jump directly before the try block, enter the try block, and then inside the try block jump again to the actual target. So we say here, if we are in this case 1, the suspension point was inside the try block, so we have this label, we don't jump to the suspension point directly, but to the try block that contains it, or yes. Let's see this. Then we have now, I call this macro co-init x, so co-init with exception, which in addition to emplacing the buffer now also sets our Boolean flag that says, okay, after line 4, this iterator variable is now within lifetime, and after line 5, this end variable is within lifetime. Now what you see here is we have this label before the try block and then the switch inside the try block, and what you also see that instead of 1 try block, I did 2 try blocks. We'll see in a second why. But in the ordinary case, if we now jump, if we are in this case that we are resuming from this co-yield statement, then if we first jump to line 8, we ordinarily go through line 9 and 10, enter those try blocks, and then in line 11, we switch again, go to our label for the actual yielding, and everything works as it should. So this is an approach that you can use here for this, how do I jump into a try block? And this is now basically the same as we did previously. We have to initialize some variables, then we yield something, but now when we explicitly destroy, we also do this in line 14 by this destroy unconditionally macro, which says, I know that this thing is within lifetime, so I don't have to do this if check, but I have to set this flag to false such that later calls in the exception handling know that this variable is no longer within lifetime. Now, what does our inner try block do? What does our outer try block do? The inner try block just is responsible for destroying all the variables from the scope. So we have to make sure that if we have an exception caught in this try block, that every local variable from this try block is destroyed in the inverse order before we handle the exception. And I did this in the inner try block mostly to also not we need this in any case because it's easier to do it in 2 try blocks and then rethrow, because then if you have multiple, for example, if you have multiple catch blocks, you don't have the code duplication.
It's correct that we basically should write this internal try block everywhere. So like if we had some local variables in the outer catch block in the original code with coroutines, then we would also need to add try block here, like around lines 20, 21.
Around which lines?
I mean, like if in the original code we have some local variables and awaits in line 20, let's say, in the catch block,
You cannot have this. You cannot. Inside a catch block, you cannot do co-await and stuff. That is one of the things about coroutines, that in the catch blocks you cannot yield. So that is the one place where we don't have to arbitrary magic.
Okay.
But if that were, which I'm sure there is a reason, that somebody at this conference can tell you why that is a reason, but you can't, and so this is nothing we have to deal with. But excellent question. Yes. But everywhere where exception can happen, we have to think about if we do the right thing. Yeah. Okay, but because this is actually a nice thing, because this actual catch clause, we can leave it almost as it is. So yeah, that is the one thing where we don't have to like modify everything. Yeah. So this is roughly how we do exceptions. Now, some small things that don't fit into a separate example. So things we cannot do. We have a local variable in our coroutine that is a lambda. And the problem is, of a lambda, we cannot know the type. So we cannot really name it to make a buffer for it and do explicit placement and after placement and destruction there. But what we can do, at least a lambda has an equivalent rewrite as this closure struct, and we can just write the closure struct somewhere, increase our boilerplate, and then use that. So that's just a mechanical problem, no conceptual problem. Same goes for range for loops, because range for loops have an equivalent rewrite with 2 or 3 variables, that you can also first do this rewrite, that you have an explicit loop with explicit iterators, and then do this rewrite, because there's hidden local variables inside there. Now there's this thing: if in your co-yield statement you do complex expressions, there's one issue. Like if you assume that this f, g, h, this operator plus, that this all gives us new objects, new temporaries, we have to keep them alive manually. We also have to destroy them manually, but we have no way of knowing which is the correct order, because like for function parameters in general, the order is unspecified, or can vary from compiler to compiler. So this is the one thing where like the source to source transformation gets to its corner. But what you always can do like is, you can do the line before the co-yield, compute the simple expression, the single variable that you want to yield, and then yield this, and then we can rewrite this. Because also this is the part where I said where the bugs are if you do a co-yield, a co-await of complex expressions with things. This also where in GCC in the early days there was it, yeah. And I can understand after doing this why this is exactly the place where the bugs were, because this is also the place where there's so many cases that can go.
What is the precedence of co-yield? Does it bind to just f or the whole expression? Like, do we yield f or do we yield the whole view expression?
That is a good question.
Because like if we
I'm currently not sure, but then you still think then you think parentheses about the whole thing, and you still have the problem that I wanted to point out.
But if we only yield a single value, then it doesn't really matter whether it's being calculated from. Oh no, it matters, because we should destroy temporaries after we yield. Is that right?
We have to keep everything alive until the semicolon, and the semicolon is actually not only reached after we have possibly suspended and then resumed. And that is the whole issue why this is an issue.
Okay.
Yeah. Because the reason is, for example, many generator types, the co-yield takes a reference, just stores a reference, which then only works if while you are suspended, you have the thing kept alive in your coroutine frame, because otherwise things are dangling. So yeah, that's an issue. And there's one thing that is really nasty, and that is fundamental in the ABI, because assume that our yield value function takes by value, and now the problem is, if you have complex by value parameters, those have to be kept alive not until, for a function, those have to be kept alive not until that function returns, but again until the full expression in which that function call is enclosed, and this function parameter object is always inserted by the compiler. So we have no way to manually manage its lifetime if we are in a source-to-source rewrite. It's just fundamental. If you have a function that takes a string by value, and the function that does the same thing that takes a string by r-value reference, they boil down to the exact same assembly because this difference is done by the call side and not by the function, and so we have no way of doing this. My take on this is functions that take parameter by value and expect in their semantics that it's important that it is being kept alive for longer than these expressions. Those are legal, but probably you should not do this because that's, yeah. But it's the one thing that you cannot give the exact same semantics if you're doing source-to-source rewrite because that's so deep in the compiler.
Even if you take object by value, but the copy doesn't do a deep copy. Because if you do a deep copy, you don't care about the caller. If you do a shallow copy and you rely on the lifetime of the caller, that's what you mean?
No, I mean you can write a function that takes a string by value and
Yes.
returns a string view from that string, which is obviously it looks really, really wrong because this looks really dangling. But if you use it while in the outer context there was not yet the semicolon, it's perfectly valid if you use it while this. And that is a...
Oh, I see, okay.
Yeah.
Because all temporaries live until the closing semicolon.
Until this closing semicolon, which in coroutines can be really, really late after we've been suspended and everybody else has done a lot of work. Yeah.
But so, since you do, like when you write, you shouldn't write this function because
You should definitely not write this function, yes.
you don't control the call. Somebody else might call it without the expression, and
Yes.
then they're dead.
If you write this, then you should better be like so junior in your career that you have someone that still flexes for you and tells whatever you do with this is not a good idea yet. So that's why, yeah. But technically, we'll do the whole thing. Okay. Now, really quick, also because of time of slide, what we can do, what we don't have the time to go into detail. Until now, our rewriting was minus bugs, exactly the semantics of C++20 coroutines. But as we do everything ourselves, we are not bound to doing everything according to that semantics. Because in particular, if you think about coroutines, they are stackless. This means they have a heap allocation or some kind of allocation via some kind of allocator. In theory, you can use heap allocation elision or your compiler can use it. In practice, that is really unreliable and almost never works without generalization. And in general, coroutines are type erased because every generator that yields int has the same type, no matter what is inside the coroutine body. And type erasure and indirection also always makes it harder for the compiler to see through the whole thing and to inline it. And this means that, for example, in particular, a generator like the simple iota generator will have so much overhead that you cannot use it in a tight loop and would always have to use a range or some other means that is not type erased and heap allocated. But we can do this, namely as follows. We make a coroutine that in the coroutine handle, it's not a lightweight handle, but it stores the whole frame, meaning that the coroutine handle is now templated on the frame. And then also the generator is not generator of int, but generator of int, comma, the concrete coroutine frame. If you think of it, this is exactly the same as with ranges, because if you think of a ranges transform view, every transform view has basically a different type because it's always templated on the functor it transforms. And this is the what we would reach by this. We saw. Then of course the good thing is I did some examples there. We need to change the infrastructure, but the concrete rewriting of the coroutine body, this can stay the same. So it's a change in the thing we have to do once, and not in this thing you have to do every time. And then I played a bit and I got it to get this performance of this IOTA generator exactly to the same assembly as with handwritten std ranges, but only after doing some tweaks to the generator class. Ask me this offline, and unfortunately, only so far, only on Clang GCC, I've still refuses to do all the optimizations, but I still don't know what it is. But if the point here is, if you have some mechanism to like do this reflection, this lowering on the coroutines yourself, you can also do it differently if you are not happy with the way they are.
Another question.
Yes?
Can you do it in other way, like, I don't know, allocate some huge buffer at the top of before the calling coroutines, and then store everything like in heap in this huge buffer?
This is what you can do with coroutines. You can do like a stack buffer, and then do a custom allocator for the coroutine that says use the stack buffer.
Yeah.
But then still, the compiler will often not see that this indirection into your buffer is something that can completely inline. But it helps with, you can do this if you say the thing that I can do is the heap allocation because I'm on an embedded system. That's a solution for this, because you can use custom allocation. But the thing is, I want to, this is just IOTA. I want to have this boiled down to for assembly instructions in 2 registers or something. Mm-hmm. This is the thing that we then still don't get typically. Okay. Yeah. Okay, so far we have done a lot of things manually with a lot of code, very tediously. Hopefully this was in some kind of interesting or maybe even inspirational, but it's not something you would do in your everyday life for good reasons.
And at this point, do we even want to be? Do we even want to follow this like C++20 coroutines design? Yeah. Because we might as well do like our own simpler coroutines.
Exactly.
Like without all these like macros. So like you can write IOTA generator as a simple struct with like next function that contains like its internal states that returns you a single value. So you might it mightn't be as combinable probably, but is it important?
There is approaches like this that you get it, but in my case, where I came from, this C++20 to C++17 rewrite, we had complex coroutines where you have like multiple phases of things. You have some initialization, then you have some middle part, then you have some end part, and those have to communicate states. So some state from the initialization that yields some value goes to the middle part, and rewriting this manually is with some state machines. This can also get very, very ugly, like writing, and because if you write ranges, writing ranges also has a lot of boilerplate. But yeah, you can, if you do things yourself anyway, you can do whatever you want. Like,
but if you say you go back to C++20 coroutines, you can migrate roughly easily with this solution? You saying? Well, still there are.
What do you mean?
The migration cost, like you can easily use C++20 coroutines on this code now.
Like to undo this?
Rather, I don't know, replace a waiter that you created.
I can show you the next slide. So this is about this, because obviously what we saw, this manual rewriting is very tedious, very error prone, but it's very mechanical. It's very rule based. I see, for example, if I see a local variable, then I have to check the type, have to check if it's like a temporary materialization. Then I have to add a member to my coroutine struct and replace basically the initialization by coinit and all accesses by coget. Really mechanical rules. And for mechanical rules, we can, in principle, write tools that do the work for us. So, if you think of it, it's some kind of very elaborate reflection. You see what is there, and you make something other from it, but according to rules. Obviously, the question currently is it desirable to even strive, to even aim for this, to be ever done? Because what we for this need is basically the whole AST and even more And the question, that's the question. Like, even if we think what kind of transformation we want, would this be too much to expose basically the whole AST and maybe even a little bit more via reflection I thought in 200 years, until I found out that 200 is not divisible by 3, so it would be at least be 201 years. But we'll see, as these are interesting times.
It will not be cplusplus17 if you use reflection. It will be not cplusplus17 if you use
No, but these things, I mean, this is just a thing, but because if you will have reflection that can do this, then we'll never have to do that with a reflection that can do everything, that will never have a core language change again, and everything becomes a library. But this is then a philosophical offline discussion.
You fall from that reflection.
Yeah. But a tool that we currently can do is libclang, because in Clang you have all those tools that give you access to the full AST, and then you write from this AST, you write basically new source code, which is exactly what we did. We analyzed our code, and then I wrote a tool, time goes, and this tool currently, what we haven't talked about, in general, it does the same thing that we just did, but manually instead of automatically. We did not talk about templates. Templating, was we've also heard sometimes this word, templates at definition time, or you cannot do much because, yeah, it's really, you cannot really say what, if you have some dependent type in there, what is it? You can track it with some cascade of decal type, val and things, and then still do you know, is this thing, depending on my temporary parameter, will this be a temporary, will it not? It's really hard, and I'm not sure it's possible. So what I did instead is say, I track the concrete template instantiations, which can I do, whether they are explicit or implicit, and then those are explicit template instantiations, those are concrete functions with concrete types, and you can rewrite them as usual. And also limited to, because of this thing with complex expressions, evaluation order, only co-yield something that is a single variable, best an L value where I don't have an additional temporary. So I have, exactly the time that I need to demonstrate this. If I find my thing here, so I have a make clean, I have here a simple example, which is now what we have not seen so far. This is a struct, and this struct has a member function, a non-static member function, which is a coroutine, and this non-static member function is templated and does something with exceptions, as we saw. So we have everything what we saw in our example plus a little bit more. Okay, so what I'm going to do this, I first, it's called create. My tool is based on Clang, so these Clang tools always need a compilation database. So I first run cmake just to get the compilation database, and then I run my tool. Sorry about the noise. It's just I have some tool based on libclang. It takes the compilation database, takes the tool, takes the input file, takes the name of the output file, and then I run Clang format. Now we can look at this. We have a generator in example. I'm very sorry about this. Let me just turn off this noise because it's really ugly. So now it should be quiet. So what we have in there, you see it's gotten longer. Okay, we have our struct. Let me check. Let's at least get 9 numbers. We have our struct. The tool currently leaves the original coroutine behind an ifdef, but else what remains is here is only the declaration, because the definition we said we want to rewrite the explicit instantiations. And then out of line, it picks up that in our main function, we use this template with the type of a std array with four C style arrays. So we have the concrete template instantiation here, which is inline. And what it does basically, the tool does not have exactly the same syntax as what we saw, but you still here see in line 54, you see we also have now the this pointer or the self pointer because we are a member function. This is also what you have here. Then we have our function parameters, line 56 and so on. The constructors, some buffers with some lengthy types because the Clang tool out of std stream makes the long version for this alias, but if we do it mechanically it does not do. We do not care. We have our flags, some storage for awaiters. We have this function that in case of exceptions like checks for all the variables whether they still have to be destroyed. Okay, our destroy function. We have one suspend point, which has some things involved here, and then we have our resume function, which in this version of the tool is still called do step impl. Here, just if you see in line 140, here you have our we have again this case of suspension point inside the try block. So we have this go to target before the try block, and then the sub switch within the target. We have some our usual, everything becomes co-init and co-get. We have a co-yield, destroy unconditionally of everything that is inside here. Catch clause, and then the co-return. So you see, minus the things that the syntax has involved as I was writing the code, this does basically what it does there. Of course, I took an example that works. So this tool is far from complete. So that's why I only showed you in the last 5 minutes, because that's not the main point I'm selling you. So let's see what it should do. We have our array. We have 13 and 17, which can be parsed as an integer. Then we have potato, which should throw and therefore break. So let us see. And what we'll do is we'll compile it in C++17. If you see standard C++17, also sanitizers. I did the pedantic, that is really C++17. The pedantic gave me for free that it does not like if I do variadic macros with 0 arguments, but this is not the thing I cared about. Now let us run this. Now how is this called? Generator example rewritten. And it works in C++17. We had the number 11, which is in hex is D, prepended by the 0x. We had the number, what was it? 13, which becomes, as 17, which is 1, 1. And then the third one was the potato, which through the exception, and the what of the exception is locked, and we break, and the what is S2E, because that's where the exception was from. And it's not exhaustive, but at least for this simple example, the address sanitizer did not immediately get really unhappy. Okay, this leaves us 2 minutes and something for questions. Thank you very much so far.
So it was a project that you tried to rewrite from C++20 to C++17. Did it succeed? I mean, rewrite, was it successful?
Oh, the whole project, yes. The parts of the software that this customer cares about now can be compiled with what did I hear with C++16, which is the subset of C++17 that GCC 8 supports, which is almost everything. Yeah. And I'm glad that it's done, because that was a intense time. Yeah.
So if you're generating this automatically, would it be possible to avoid the destroy if constructed tracking if you put a try-catch block starting immediately after the initialization of every variable? Or does that cause other issues?
I'm not sure, because I think it's always the issue that you have, like, inside your try block you cannot jump, and then it would. I don't know if it would only get really messy. Yeah, but the point would be, like, for every local variable we would have to a switch case jump thing, because you cannot jump in there. And maybe it could be doable, but if it would be practical and better, I'm not convinced. Yeah.
Well, let's see. So the chain of jumps the compiler should be able to see through and optimize. So you would definitely not want to write this by hand. The question is whether, for automated generation, whether it's viable. And it avoids keeping extra state.
Yes, but things that the compiler sees through, those also have a limit. So we would have to try this out. Yeah, I'm not convinced that it's better because like a coroutine in general has a little overhead. And typically, if you are in this coroutine type erase thing where you do this large batches, then this setting some bools to true additionally is probably not something that shows up additionally. But what you of course can do is like you make this infrastructure to say, this is no except, I use the no except infrastructure that does not do those things, and that way opt out it that such that I don't have to do this for a simple integer manipulation. That is the thing that you can do and that I have done and which is easy. And also say I have a variable like an integer. I do not care, it has a trivial destructor, so I don't do anything, I do only something for the constructor of like types that are not trivially destructible. Then also the constructor is probably not that trivial and and this additional bool write amortizes. That makes sense. Yeah.
So this tool, do you have to tell it where the coroutines are, or does it just go to a batch of files and replaces them all?
This does automatically the Clang. You can write this matcher, which says give me all coroutines basically, and then rewrite them. But you have to go through all the files. It's really, those tools are really expensive. So maybe if you can do like a check that like you only files that grep for co-yield or co-await or something. This is what you can do in practice if most of your files don't have coroutines, just to save time. But typically it does this also detect this.
You mean expensive runtime?
It's expensive because because these Clang tools, it does a full analysis, basically half of the compilation, it does it itself. So those tools are, really powerful, but it's, they have some runtime overhead if you run them like in a continuous integration on a large code base. Yeah.
What do you do with the converted code? Like, suppose you found a bug and you now need to change this converted code. Maybe you need to add a new variable. Like, do you write all these new try catches yourself, or do you update like the old coroutine style code and then apply the tool? Like, what is the support process here?
I have this. So this tool is not that far, but I do it for a simpler thing for like rewriting using a num C++20 feature, but much simpler C++20 feature. I have such a rewriter. What I do is like I write the C++20, but I write C++20 where the continuous integration checks that automatically it can be rewritten. So I have a continuous integration that takes the C++20, runs the tool to make it C++17, and then checks whether this rewritten code can be compiled in C++17. So you don't want it to converge. The source of truth is the C++20 tool, and either there's a bug if there's a bug in the C++17 tool code, there's either a bug in the C++20 code, then we fix it there, or there's a bug in the rewriter, then we fix it there. So this is just the symptom, if the bug is only in the 17 code.
Oh, so like you basically provide your client like a half compiled project, meaning like in C++17. It's like one of the artifacts is C++17 code. So you don't like manually just convert it from C++20, and then you also ensure that it is always possible to do so. It's part of your build process, essentially.
Yes.
Lovely.
And we are hoping that they said that they're discussing to update their toolchain such that they can have a compiler soon that is based on GCC 12. So then I'm happy to, although it was half a year of work, to unroll all this again, because that's like sunken cost fallacy and all this. Yeah.
So you don't support any C++17 code yourself except for this CI check. You don't have to write it manually. Like you wrote it manually.
Most like 98% we wrote manually, and like this one feature is currently as a proof of concept is automatic. Maybe we can write more checks. For example, for like defaulted equals operator is also something that is like bounded in scope, and then get back to the C++20 solution, which is just nicer. I really got to appreciate C++20 while I was getting rid of it, I have to say. Yeah, I think then let's get some coffee. Yeah. and I'll also be here for the whole week if there's some offline discussion. Thank you.